Heading of a boat. In this exercise, we consider a boat moving in the waves, and we have to estimate the Euler angle from two sensors, the magnetometer and the accelerometer. The accelerometer will give us the vertical, and the magnetometer will provide the heading. What we call the magnetic dip or inclination is the angle we have between the vertical and the magnetic field we measure. So there is a relation between the latitude and this angle, which is given by this formula. So in Brest, the town we consider here, the latitude is given by this angle in degree. And if we apply this formula, we get an inclination of 1.15 radian. For the visualization, I propose the following program, which uses the Broblib library, and I will draw the boat with two arrows. So this arrows in magenta corresponds to y and the magnetic field, and A here is the acceleration we measure, and it is related to the gravity. Normally the acceleration we measure, so given here, should be something like 0, 0, and 9.81. But here we do not consider this, we normalize and we put 1 here. So it is the acceleration we should measure if the orientation corresponds to the identity. Here I correspond to the dip, to the inclination, and this one corresponds to the magnetic field we measure if we have an orientation corresponding to identity given here. So this line draws the boat and the magnetic field and the acceleration when we are at identity. Here it is the position of the boat. So we put here 10 instead of 0 just to make a difference between to avoid the superposition between the axis we measure at 0, 0, 0, so we draw at 0, 0, 0, and the boat itself. The program is given here. I will run it. And I see this picture. So we have the boat. In magenta, we have the magnetic field. The angle between the horizontal here and the magnetic field corresponds to I, the inclination. And here in black, we have the acceleration we feel. Here in gray, you have the shadow, so it means the projection of the boat onto the ground. Here it is a 0 point, so normally the boat should be here at 0, but to avoid the superposition, we put a z equal to 10. Here it is the boat, which is represented here. I have the x-axis like this, and the y-axis like this, and the z-axis like this. The rotation matrix corresponding to this orientation in this picture corresponds to the identity. So 1, 1, 1, 0, 0. Okay. Here we have the north, here the west, and here upward. This angle here corresponds to the inclination I, and this one corresponds to the acceleration A. So if I am here in Brest, let's say here, Brest, then the axis, the frame R0, so R0 given here, is like this, the latitude corresponds to this angle, corresponds to lambda, and the magnetic field is like this. And again, this angle corresponds to I. So about the dip. When we are near to the equator, it will be parallel to the horizontal. Here, the magnetic field will be like this. Here, like this. And at the North Pole, it will be like this. Okay. Enter like this, enter like this. Okay. Now, I recall the relation I equal arctangent of 2 tangent lambda. In Brest, the latitude is this, and I is equal to 1.15 radian. So what we should do in this exercise is when the robot here is able to measure in its own frame A1 and Y1, so the one means in its own frame, we have to build a system, so it's usually called IMU, which provide an estimation phi, theta, and psi of the Euler angle. Okay. So, question number 1. From A1, we have to provide an estimation of the pitch angle, or the bank, theta, and the elevation, so the roll angle, phi. If Y0 is a magnetic field in the world frame, then we have Y1 is equal to R multiplied by Y0. So this one is a magnetic field measured by the boat. And here it is the orientation of the boat. So R is equal to depends of phi, theta, and psi, the Euler angles. The same for the acceleration. If A0 is the acceleration that should be measured if we are at the orientation identity, then what measures the boat is the multiplication of R multiplied by Y0. By Y0, A0. So we'll try to show this on a simulation. I consider the following program. The acceleration when we have the orientation identity. This one, the magnetic field in the same condition. And for the visualization, I put a loop where I made a variation here of just phi, the roll. And then after I will switch, I will move this one only, just for the visualization. So I build the Euler matrix, which depends on phi, theta, mc, the three Euler angle. I build here A1, Y1, and then I visualize them. I represent the true boat at this position, and also I shifted here to represent the other boat, where the orientation is identity. So this one corresponds to what is seen by the robot in its own frame. So we just have consider the orientation. This one is just for the visualization to avoid the superposition. And this one is what is seen in the world frame. So I will run this program. And here I can see what we have when I move the roll only. So we can see that the magnetic field here and the acceleration here corresponding to the vertical or the gravity. And in the frame of the robot, it is represented here. So in the frame of the robot does not move, but we can see that the magnetic field and the value given by the accelerometer change this time. For the estimation of the roll, I have represented the boat in two frames. Here it is R0, the world frame, and here it is the robot frame, R1. Here the acceleration A0, and in the robot frame it will be like this, A0. Now I will have also here the vector I represent J, which corresponds to the left of the robot. And so here it will be like this. And what I want is to compute this angle, which corresponds to the bank. Okay, like this, phi. So we understand that we have to build the scalar product between A0, which is normalized, and J also, and we get that phi is equal to, so I built the scalar product, which corresponds to the cosine of this angle. This is why, since I want this one, I will take the arc sine of this, and I will get an estimation of phi from this one which is measured and this one which is known, since it corresponds to 0, 1, 0. Now I will do the same with the pitch or the elevation. So for the elevation, I will have here A0. So this one is a world frame, and here it is the boat frame. So A0 will be here, and this one we understand that in the robot frame it will be like this, A1. What we want to find is theta. So I will do the same. So I will be like this, or like this. And what I want is this angle, which corresponds to theta. Maybe like this, since it is positive in this representation, even if the scalar product is between I and A1 is negative. So due to this, I have theta equal, so I make the scalar product between I and A1, this vector. I will take the arc sine, and since this angle here is positive, whereas the scalar product is negative, I put here a minus. I will provide a simulation for this. So I propose to take the following program. And the bank is given by this formula, the elevation by this formula, and I will see the difference between the actual Euler angle and its estimation. We understand that the bank and the elevation only depends on A1. In the simulation, only the roll is moving, and I can see that in this situation the error between the true bank and its estimation is equal to 0. Okay. So it means that in this situation the estimator works quite well. Now, instead of making moving only phi, I will do the same but with theta, like this. I will draw here the estimation, and I can see here again that the estimation is good. Question number 2. I have to compute the orientation which leads our boat to the nearest horizontal orientation. So this will be used to get the heading. So in SO3, like this, SO3, which corresponds to all orientation, I have a curve like this corresponding to the set of all horizontal orientation. So due to the waves, my boat is not on this line, it's not horizontal, it is here with orientation matrix R, and I have to compute the transformation RH, which provides me the projection. So for this I have to recall one thing. If I have a vector u like this and a vector v, both are normalized, have a unit norm, then the smallest rotation, also the rotation, shortest rotation, the one which is near to the identity, which transform u into h, will be a rotation with respect to the angle which is orthogonal to u and v. So rotation with respect to u to this vector product between the two. And now I have to find the angle, and of course the angle will be related to the cosine of u and v. So for this I have this formula, which is rather intuitive. Okay. So I take here, I build this vector around which I have to rotate, and I have to normalize it. Okay, this is done here. So this is a unit vector, and I have to turn with respect to the arc cost of the scalar product between u and v. Then, using the Rodriguez formula, I take the exponential, and it will provide me the rotation, the shortest rotation, which will transform u into v. And this one is called RH, because I will have to transform a1, the acceleration, into a0. Now, this formula is singular when u and v both match, corresponds to the same to the same vector. So it means when my boat will be horizontal, then I will have a singularity. This is why I prefer to use another formula, which is not explained here, which is given here. So this one has an input u and v, and will provide me the same rotation matrix, but without any singularity. So to draw what we call the horizontal avatar, it is a boat which corresponds to the horizontal projection of the actual boat. So for this I will only use A1, which is measured by the accelerometers. I compute this one. RU and V correspond to this function, which is in rublib. And then I will compute the orientation of the avatar by this multiplication, and I will draw it. So this is my program with draw avatar here, which is called inside the loop here. If I run the program, I obtain this. So we can see that in magenta, I have the projection. Okay. So here in this program, I only made a variation of the role. back here, and if I provide a variation of the pitch, I run it, I can see again the avatar in magenta. Question number 3, I have to provide an estimation psi hat of the heading angle psi. So what we do here is that we transform the vector A1, H1, which is the magnetic field measured by the sensor in the boat frame. Then I will transform it to see what is seen by the avatar. So I will call it YH, like horizontal. Okay. Then I am now in the horizontal plane, and I can get the estimation of the heading psi hat by taking the arctangent 2 of this, the two first component, H2, H1. Now, due to the fact that I am in a frame which is north and west, so from the top, and usually we prefer, we understand the angle in this direction, like which is the opposite, so this one is direct and this one is not, then I have to put a minus here, otherwise I will have a problem with the sign. So I prefer to have a positive sign in this direction. I take this program where I have here the procedure for the heading. I will run it with a variation of phi only. If I run it, I can see here that I have a good estimation of all Euler angles. I will have also a perfect estimation if I change just theta, like this. But if I change both at the same time, then due to the fact that rotation matrices do not commute, then I will have a small error. We can see here some small error, but it is acceptable when the Euler angles are quite small.